So, am I actually, wait, was it showing me talking? Now it is. Okay. So, anyway, thank you for showing up again to today's beginner lectures. So, a little bit of a change. I usually go over, who's this? Hello. Lectures. But since graphs are a little complicated, what?
Feedback form, but we can do it after.
What do you mean?
Feedback form.
What?
Feedback form.
Oh yeah.
No,
I can talk about it right now.
We'll do it after, because do we want to do it now?
Okay. So we'll do it after. Something Lazaro wants to talk about at the end of this lecture. But in any case, it's going to be a little different because graphs are hard. They're not exactly beginner friendly. We've discussed this with the rest of the e-board. So it's beyond the scope of these beginner lectures. So from now on, we're going to go and discuss graph problems on LeetCode. That sound good? Okay. So actually, can you hand me my phone?
Yeah.
So I know which question it is. Take a picture of it. Okay, so the question I want to go over on LeetCode, it is this one right here, 7, 3, that's a 3, network delay time. All right, who's seen this problem before? Anybody here seen this problem? Okay, well, I'll describe it, and maybe you have. So you're given a huh?
Oh my god.
Well,
Okay.
this is a hard problem, but we're not going to go over the concept. So I guess
Then how will they understand it?
that's a good point. Okay, what do you want to do?
Something that is easy.
Okay.
Island perimeter?
No. Actually, can you find min courses?
I did that one.
You did that one?
Island perimeter?
I did it.
No, num courses. Sorry.
None courses?
Yeah, num courses.
I think I did. Wait.
Some problems there.
That's not what they want.
What do you guys want to do that's graph related on LeetCode? What is it? Minimum path? That's actually what we were going to go over right now. It's actually this. Well, not. Well, actually, yeah. That is what this is. This is Dijkstra.
Yeah, it is.
This is a Dijkstra. So they're saying Dijkstra.
Alright, then go ahead and do it.
Then I'll go ahead. But do you guys want to do Dijkstra? Single source shortest path?
In graphs?
Yeah.
Sure. Yeah.
So basically, you have a bunch of nodes labeled 1 to n. N is your input. So that's going to be the function. And per an example, I'm going to say we have n equals 3. We have node 2. I'm doing exactly how they have it. 1. I think this is 3. I think this is 4. And I think they're all 1. Okay. So let's say node 2. Oh, okay. And of course you have start. Or k. You have k. And let's say k equals 2. So k is the node that wants to broadcast a message to all other nodes, right? Assuming it can get to all other nodes. So we're going to check that. And so we want to say how long is it going to take for node k, which is 2, to send this broadcast, this message throughout all the network of nodes. Oh, I made a mistake before. Yeah, okay. How long will it take?
There's two nodes.
What?
The first one is the one to the left is 2 and the other one is 2 also?
Oh, okay. This is number 2. This is number 1, actually. It's 1 to n, so 1 to 4. So how long does it take to get from 2 to all the other nodes? Oh, so this is a directed graph, just pointing it out, and it has a weight associated with it. And the weight is how long it takes to get, well, from one node to the other.
So you're asking from 2 to where?
All of them. How long will it take?
Like 1, 1, 2?
So it takes 2
The max to 4, yeah.
to 4, right? Because that's the furthest one.
Yeah.
Okay. So we want to see something?
So you're asking for the minimum time it takes to reach all nodes.
Oh.
Yeah.
So if 1 second passes and we're starting at 2, we have seen 1 and 3. Right?
Yes. So at second 0, you see 2. But at second 1, you see 1 and 3. And at second 2, you see 4. And there's no more. So it takes 2 seconds to get from 2 to all other nodes to broadcast the message or signal or whatever. All right? Do we get the goal of the problem? Okay, so how do we go about this? Actually, let me just, do you think I should use that one? It's going to be a little.
Yeah, for dice strokes, that's pretty smart.
So I'm actually going to use the big board because it's going to be long. So this is, so actually, before I go on, what kind of a problem is this, other than it being a graph problem?
DFS.
No,
You could.
I mean you could use it, but it's a little more. It's not DFS.
Backtrack?
Backtracking? No.
I think the DFS part is backtracking.
Yeah, there's not really any backtracking here. Okay. So this is, well, correct me if I'm wrong, this is dynamic programming, right? Because you have to retabulate, costs associated. Actually, do you? Yeah, you don't actually. Never mind. Disregard what I said. Disregard what I said. I think that applies to, but for other graph, for all pairs, it's dynamic.
Yeah.
Okay. So is this an all pairs shortest path? Okay, you don't know. They don't know what that
You
is.
start from the beginning. Dice
Okay.
strokes. You just explain dice strokes.
So this is a single source shortest path, right? So it tries to get the shortest path from one source, one node in the graph to every other, right? Okay, and that's basically what you're trying to do. And usually you would tabulate that, right? You would say you'd have a distance, right? And you say at k, which is 2, the distance is 0, like I did before, remember? And then for everyone else, we go through the graph, right? Okay, where's the eraser? It's back here. Do you think red, can they see this? Or is that like too light?
You can definitely see it.
They can't see it?
No, they could.
They
Do
could.
you want to try another marker?
Try black or blue. No.
No, yeah, go with black.
I go with black?
Just stay with the red.
Oh, wow, yeah, okay. I'm sticking with
Oh, actually,
this
don't do
one.
that at all.
What?
Okay.
Don't freak me out, dude. Come on. Okay. So, actually, let me put this here, that one there. So this is what they give you.
Wait,
Yeah.
are you going to explain what single source means?
Okay. I did. I just did it.
You can explain dice strokes before going into this?
Okay.
Just give us one example.
Basically, what you want to do, right? At first, I guess I'll just do an example.
If you give them dice strokes, like the algorithm for it, they'll be able to figure this out.
Is this the first time
time that you've seen single source shortest path in the beginner lecture?
But this is the first time we do beginner.
We've discussed Dijkstra's before, single source shortest path,
You
but
said the name, but this is the first time we do beginner lecture.
yeah, this is the first time we discussed it here in beginner lecture. If we could do that.
Perhaps you'd want to explain exactly what it does.
Yeah, I think you need to do that.
Very good.
I'm going to give weights associated to it, so it doesn't matter. 2, 1, 3, 1, 7. I'm going to give this one. This one a 4. Okay. So let's say we have our S, right? And our S is 1. So this is our source. So the distance we tabulate at first. And I actually just have the table. For 1, it's 0. Because the distance from 1 to itself is just 0. Well, then we start off by saying that for everyone else is infinite. Because we just say that we haven't calculated it yet. Also, the reason we also say it's infinite is that maybe it's not reachable at all. Maybe the graph is completely disconnected. It's not a connected graph. Yeah. It's not a strongly connected graph. No, I don't think that's...
I think strongly
it's-
connected is when all the nodes... Wait.
There's multiple components.
Okay. There's multiple components and they're not really, it's not connected very well. So maybe 1 cannot reach 6 because of this. But, you know, we'll just say, I have an eraser. Why not using it? Okay. Come here. Also, it's the shortest path. So what are we going to use all the time? A math. Use min, right? We're going to minimize. We're going to minimize this.
It's called a connected graph.
Okay, it's a connected. Yeah, that's what I was saying. I said
Yeah,
connected.
it's
Okay,
like-
all right. It's a connect. If it's not a connected graph, then some of them might say infinite. But this is a connected graph, and 1 can get to every node conveniently. So this is good. So also, then we have to color them too. Nope, actually we probably don't need to do that though. No, we don't. Actually, yeah, we do need to do that.
You use a set or something like that, so you know not to revisit it.
That's the thing. You might want to change the value again.
Do you revisit a node? That path is a bit inefficient.
That's for cycles.
Maybe just copy it. It's a little too complex.
It is a little complex. I also have to talk about min heaps. That min heaps are important in this one. Yeah. You guys know what a min heap is? Okay, you know.
Tree with the minimum.
Okay,
Like a full tree with the minimum.
it's kind of like a tree. It's structured like a tree, right? But it's really an array, right? And the left child is 2 times that index value, or 2 times it plus 1. It depends if you're doing 1 indexing or 0 indexing. If you're doing 1 indexing, the left child is times 2. And the right child is times 2 plus 1. But if you're doing 0 indexing, it's 2 times index plus 1. And the right is 2 index plus 2. Are we still?
Like
Just
on
to follow me
LeetCode,
along.
when you're given a tree as an input, the way they represent it.
Okay, so they might, so see, there's the thing. They might return to you a 2D array, right? Like this, I think. Yeah. In this problem, they're probably going to, so if I'm going to return this, it's going to look something like this. Like they're going to do, it's going to be 1, 2, 1, And for this one's gonna be 1. Oh, wait. Okay, no, I did it right. 1, 3, 2, 2, 4, 3, and maybe you can get the pattern. This is how they're gonna give you. They're gonna give you a 2D array, and in this problem, for instance, it's gonna be the source, the destination, and the weight of the edge. Or actually, I'm not gonna call it that. To be mathematic U to V, right? Where U and V are nodes. And this is a directed graph. If this was undirected, this would appear twice, but this would be reversed. Does that make sense? Since it's undirected, it goes both ways. Okay. So, yeah, what were you going to say? We can continue with this. Okay. I'm not going to write the code. But I'm not going to write the code. I'm going to show what it does. So yeah.
Sorry, you might want to, from 1 to 4, the path is, the sum of the paths for the for both the directed edges is 4. You might want to make it 5 to make it like a clear example or something like that.
What do you mean?
So 2 plus 2, 4, and 1 plus 3 is 4. Just to
2 plus what?
2 plus 2.
That's a.
Oh,
That's a 1. That's a 1. Okay. Okay. I fucking gotta do this. Damn. It's the handwriting. That's a 1. That's a 1. Don't worry about it. It's something I have to work on, I guess. Well, my penmanship. Okay. They're not gonna be the same. They're not gonna be the same. So first, I think you have to have a priority queue or a min heap where the maximum priority is the smallest distance you've seen. Also, of course, when they give you the array, you might have to build it, right? With an adjacency list, and that's a hash map. And so what I would do is say, this is directed. What is it? Okay, what do you think we should do to create the adjacency list for this?
I still didn't know what it is.
Yeah, do you know what you guys know what an adjacency list is? You don't know what an adjacency list is? Okay. Basically, an adjacency list is a representation of the graph, right? It's a data structure that represents the graph. So it would be a hash map. You can still make sure they can still see me. And where the key value pairs in a hash map or a dictionary. Okay. All right. So really quick. So usually in an array, in order to get a value, put the index 0 to n. But in a hash map, you don't need numbers to get values in it. For instance, you can just put it high, right? It's 2, low, 4, and by. Okay, so this will be one dictionary or a hash map. And in order to access the value of high, right, I can I'm gonna call it D for dictionary. D, right. So what's that gonna return? Yeah. So you don't need a number. You can put anything. The point is that this will be hashed, right? And so that will point to a memory location, and it'll instantly, get it.
And it's unique, right?
It could be some like hash collision. I mean, you want keys to be unique,
Okay.
typically.
No, yeah, what you said is right.
What?
There's some collisions.
What?
Possible collisions.
Yeah.
When you
I mean, I said that.
No, yeah, that's what I'm saying. No,
You said he.
No, I said what you said is right.
Oh, okay. I'm sorry, I lost the plot. I lost the plot. Okay. But typically,
Take like a big prime number and then take the module of the number. No?
yeah. So you get like a big prime number, really, really big. You mod. So you do some math on the object, right? You mod it, and that is the memory location where you're gonna store whatever value you're gonna put in there. Does that make sense?
Memory location or index value?
I don't know. Isn't an index value supposed to be a memory location? Let's not get too complicated. The point is that this is a data structure that works. This just works. This just works. And if you don't know what you're doing in an interview, use this. This is clutch. This is a clutch data structure. What was I? Well, forgot what I was saying. Oh yeah. So we're gonna use. Well, where was I before I started talking about this? Okay. Yes. So an adjacency list, I would say, whatever that. I'm gonna make it a dictionary, right? And of course, what would be the keys? The nodes, right? So it would be the nodes. So I would say, node 1. And what would be the value? 2 and 3. Is something else we need to put in there?
The weight.
Yeah. So what we could do, it's going to be a list. And it's going to be a tuple. It's going to be destination, where it goes, and the weight. Does that make sense? Right? Because that's where it goes, and that's the weight of the edge. And do the rest. 3, and the weight is 2. And so on, until you've done it for all of them. Okay? And of course, you want all the nodes, and some of the values might be empty lists. Do you see any examples where there will be empty lists as values?
That's 5, 6.
5 and 6, because they're not adjacent to anything. They don't point to anything. All right? So that's an example of building an adjacency list where you have to do a for loop, right? Of course. And that's it. Well, I mean, just like do. I mean, we'll discuss it now as an example of how to do this for this problem. Okay. And okay. So one other thing, you do need a set. Are you sure?
Yeah. Where's this problem? Do you know? Yeah, I think
Okay. We'll see. We'll see. I mean, there's no cycles in here. This is acyclic.
Oh, in there, yeah, but you want to generalize, no?
Okay. So do you think we should do something like this, just to have a cycle in there? Okay. So I'm gonna put maybe 2. I don't know. You just want me to put a cycle in there, see what happens. Yeah, there is a cycle now. It goes like that. Okay, so and at first all the distances were negative, right? So then we have our priority queue, which we first instantiate with the lowest one. Of course, you know what? We don't need a priority queue necessarily. If we just have the set, right? We can just change the value here. Yeah, this one is a hard one. This isn't a complicated one.
What's the difference between priority queue and maybe and a heap?
They are the same.
They're the same?
Yeah, they're the same. I just said priority queue and min heap interchangeably. Wait, do you know what a min heap is?
You said that it's like a tree, except explain except.
It's like an array,
Yeah.
right? And then like the child is that index that I said.
Times 2.
Yeah, the thing times 2. If you're one indexing, what?
Do you want to stay with this problem? If you want to switch, I can give you a problem that had like
I was thinking of num courses.
that Google gave me.
Which one?
Keys and rooms.
Keys and rooms.
Yes.
I have never done this one.
You need to use a graph algorithm to solve it.
Can you, okay, give the
Any
problem.
graph algorithm? Oh, sorry.
No, it's. Should I say that again? That be the algorithm?
The what?
Should I say the algorithm? It's not a graph, but you do have to use the graph algorithm.
It's a matrix.
Yeah, sure. Go ahead.
Is it a matrix? I'm just, I don't know.
It's an array of arrays.
It's an array of arrays?
Yeah.
An array of what?
Of arrays.
Okay, but what's the array in the inside? Huh?
Array of arrays. It doesn't represent a matrix.
So it's just an array of arrays? But what's inside the arrays?
It's an integer inside the array. Of
Okay,
arrays.
so it's a 2D array of integers. Okay, that's what I wanted to know.
Yeah.
It's a 2D array.
Yeah, but it's not n by n.
Yeah.
What is it?
The first array can have 2 elements. The second array can have 3.
Also, it's like a disjointed. So it sounds like to me it's like a.
Dude, let me read the problem. Because it's not a graph. Okay. There are n rooms labeled from 0 to n minus 1. And all the rooms are locked except for room 0. Your goal is to visit all the rooms. However, you cannot enter a locked room without having its key. When you visit a room, you may find a set of distinct keys in it. Each key has a number on it, denoting which room it unlocks, and you can take all of them with you to unlock the other rooms.
Do you guys want to do that?
Is it like the badge problem? Remember?
Oh, well, I don't think it's a badge problem.
Really? Okay.
The badge problem was hard. No, it's definitely not a badge problem. Because that one you had a range.
Alright.
So that one you have
But
to look
without
at.
range is a. Oh.
No, it doesn't have a range. It gives you like the exact number. And you just want to see if you can access every room.
Okay. So we're abandoning this in the middle of it. You guys still want to solve the other one, or what do you guys want to do?
You have 2 more weeks of your develop. You have 1 more week of your development.
Only one?
That makes sense.
Do you want to work on that? Just vote. Yes. Raise your hand. Yes. Right now. Just don't. No, we don't do it. Raise your hand. I'm asking you guys to raise your hands, and you know.
To do it.
Yeah, to do it. Yeah.
Do you want to spend more time learning Dijkstra's and mean heaps? Or do you want to switch to something you've already learned but apply it?
I guess extra is very general, but that problem is like applied.
Yeah,
So I do like
we can do that one.
Wait, what do you mean? You mean like very general? What do you mean general?
like you find out a YouTube video on that, but maybe the keys and the logs, that's more like applied.
Okay, so I'm just going to decide that we're gonna go on to that.
That's what they all decided.
I don't know. I want it to be verbalized. Now it's verbalized. Now they've said it. Okay, so you have n rooms. N equals 10. Okay, and all the rooms are unlocked. I'm gonna say it's 0 to n minus 1.
Here, I can sticks. You can write down the first example.
Okay, 0 to n minus 1. All of them are locked except for 0. So I'm actually gonna number them. And 1 has 2. 2 has what?
3.
And 3 is empty?
Yeah.
Okay. No, it's 4. Okay, so what's the problem exactly that you're asking?
Return true if you can visit all the rooms, or false otherwise.
Oh, okay.
You start at room 0.
Okay, you start at room 0. So can you reach all the rooms? I mean, I'm looking at it and it's yes, right?
Yeah.
You go to room 0, you get the key for 1. 1 has a key for 2. 2 has a key for 3.
This is the
And that's it.
This is the adjacency list for the.
You know what? Yeah. This is basically an adjacency list.
Yeah, sure. You don't have to build it, but
Yeah, so
remember they give you an array.
so if I had to draw it out as a graph, what would it look like?
A line of nodes.
Like a linked list.
Pretty much, right?
Yeah.
So, yeah, 0 goes to 1, to 2, to 3. And that's the route you take. So can all of them be visited? Well,
Can you go back?
can I go back? What do you mean?
Can you like go back a room once you've entered another one? Is that what you asked?
Yeah.
Yeah. So like say that
Like 1 has the key to 3,
Yeah.
and then 3 to 2.
Oh, it doesn't matter. I mean, I could just, I think the problem, it doesn't matter. I can have, one can have the room to 3, 3 to 2.
0 to 1.
So then in this case, I just make it 0 goes to 1, goes to 3, goes to 2. Oh, and all of them.
You okay?
I mean, yeah, nothing happened.
Maybe
Nothing.
have more than, I mean, can 0 open more than 1 door?
Yeah, yeah. So maybe I can. It is guaranteed that there are. Like, can you have multiple?
Key opens different.
Can I have this? Can I have this?
Yeah, you could.
Oh, so that's the thing. Okay, just making sure.
What's the name of the problem?
Keys and rooms.
So, what would this look like? This would be like a. This would look like a 2. 1 goes to 2. 2 goes to 1. And 3.
So what? So 2 contains the keys to 1 and 3.
Yeah.
Okay.
So in a graph representation, you could take multiple paths. You can go like this. Well, actually, you could go in a cycle and go back and go here.
Yeah.
Yeah. Okay. Can all of them be traversed? This actually seems pretty simple.
What's the question, like the point?
Can you visit all the rooms?
Oh.
Do they tell you what room you start in, or is it always 0?
What room do you? Yeah, 0 is the only room that is unlocked. So that's the room you start in. Okay. So, what do you think, guys? Because, also one thing, do you have to follow one path, Lazaro? Is there one path you have to follow?
No.
No. So I can literally go in a cycle and then go back to 3?
Yeah, you could.
Okay.
But do you want to do that?
It's an option we could take. So, okay. So if you can't do that, then
N is the number of N is the number of doors.
no, and it's the number of rooms.
You could like
Which I think is the same as the number.
put every.
It is.
Well, yeah, you're right, but one of them is unlocked and that's 0. So you could say, you know,
What if we do like DFS where we mark them and the unmarked?
okay.
If we have any unmarked, then.
Or you could like put every key in a set, and if some room is left out, return false.
Oh. But what if we go back to the room? What if we go through a path, right? And then we end up in a cycle. I mean, I guess we could do that, but
Can we mark it?
hmm. Hmm.
So when you add every key, so it's gonna be unique. If the length of the set is less than the length of the array, return false.
The length of the set is less than the length of the. You mean this?
Yeah.
So if the length of the set is less than. Wait,
So-
why? Wait, so, well, you're gonna make a set. We're gonna make a set.
Yeah, that's one approach.
Okay, so how are we going to? Okay, so let's say we start here, and we've made an adjacency list. So what do we do? So do we add 0 to the set?
No, just the keys.
What do you mean? But we need to keep track of the ones we've seen, no?
Yeah, what we do is start with 0.
So do we add 0 to like a set, like I've seen it, a DFS, so we can color it? Well, I think 0, 1, 2. I'm gonna do 0, 1, 2, right? So I'm gonna say all of them are unexplored at first. And I'm gonna say, I guess, 0, 0, 0, 0. And now we start at 0. Make it a 1. Okay? This is just an approach I'm doing. And so now we go through the list of neighbors. The list of neighbors are 1 and 2, right? So I think DFS is actually a pretty good way to solve this. So we could take, I think we could take this path. We go from 0 to 1. Make that a 1. Oh, change it here. And then the adjacent ones, it was only 1, it's 2. Make that a 1. So should we explore 1? Yeah, we're going from 2. And 1 is adjacent to it.
No, because it's 1.
Yeah.
Yeah, sorry, you didn't do it.
So don't do anything, right? And so then I go to 3, make this a 1. 1 has no adjacent ones. Make that a 2. So a 2 here. Go back. Make that a 2. Back here. This a 2. Go back here. Make this a 2. So they're all 2s. Like we're done. Like we're not gonna use that ever again. Like remember when I was saying white, gray, black? I'm just, 0 is white, 1 is gray, 2 is black. And what black means is that you're never going to need that node ever again because you've gone through all of its descendants and you've gone back up, backtracked up. Okay, so what is it that we need to return, right? That they've all been explored. So could we just iterate through this and say that they're all 2s? They've all been explored? I mean, I'm spitballing here.
I'm trying to think of a special case. If one of them is not connected, then it's gonna have to return false, right?
Okay, so let's do this one. Let's do, yeah. Yeah, I'll just do this.
But, that's fine.
4 0.
See. And then 4, at the end of all this, right, it's just everything. And it's going to be 0. And if you find one that's 0, or I think it's just, maybe the 0, 1, 2 thing isn't necessary. We come up with a bad solution and we optimize it. But okay, so let's go with this. If there's a 0, that means that we were not able to explore it because there weren't any keys that led up to the path. Therefore, we return false. But what ideas did you have?
No, yeah. Where there's a 1.
Whether there's a 1?
What does the 1 mean?
It means that you're not done calling all of its descendants, right? You're not done backtracking to it and then backtracking back up. Okay, like blue, like white, gray, black.
So 1 is gray.
Yeah, 1 is gray.
Do we care about that?
I guess it's not really that important. This could be solved with BFS too.
Yeah, I could-
Actually, yeah.
Yeah, that I did.
That's how you did it. I mean, we're doing it in DFS, but
Yeah, I also did DFS, but you also done DFS.
you could do this in BFS. Okay.
But the better one is DFS.
It is. So this is the better one.
Yeah.
Okay. So just find one that isn't. Okay. Can one end up being 1? I don't think so. I think they just all end up being 2.
I mean, by design of BFS and BFS, none of them would end up being 1, would they?
Yeah. They would. None of them would end up being gray. They would all end up being black. Or
As long as they're
yeah.
connected.
Yeah, exactly. So you're always starting from 0, right? So when you're calling DFS, just call it on this one. And that's it, right? So basically, I think the code is, I'm going to leave that there. How do they give you? It's like a 2D, right?
Yeah.
So def solve, I don't know the name of it. N and
They only give you rooms. Yeah,
room,
you can derive and from the length of rooms.
which is, I'm going to say a list. I don't need to do this, but I'll just say a list, int. Couldn't finish that. I couldn't finish. I had no space. I'm sorry. Oh, actually, if I put it back, I'm gonna put it back. Okay, as long.
What have you guys come up with? What's the idea? You want to let me know?
We said the BFS.
BFS? Okay.
Yeah.
How are we going to use that?
We just need the ones, right? So do we need to backtrack?
Well, if we're done using that node, it'll turn into 2. But if we never explored that node, it'll be a 0. I don't think it matters. You could just use 1 or 0, right?
That's exactly it. It only needs to be boolean.
Okay, so basically, guys, you don't need what is it? Yeah, you don't need. You could just put, like, I can put all these ones.
Yeah, I was gonna suggest that you could just literally set them as true, or like keep them as true as you go along.
Okay.
And then,
And another thing we could do is we can just make an array. We don't need a hash map
Yes.
because it's 0 to n minus 1. So we make a new array.
The reason we don't want 1, which is that value for, like, saying we're processing it, is because if we reach that node, then we know we've already seen it. So there's no need to do it 1. Just return there.
Right. So if you find a 0 or a true or false, it doesn't matter. Then if you find one instance of a 0, that means it's false, right? But if you don't, then just return true, because that means that you've explored all of them. Okay. So they give you n and they give you rooms. This is rooms. So the extra data structure you need is an extra, well, first of all, you need the adjacency list. So list, I'm gonna make it, what?
You don't need that either.
You don't need that either?
You can use indexes.
Oh, okay.
Because the values within the array, it represents an index.
Okay. So, but you do need this one.
Yeah, you know, you do need that.
Self, I'm gonna call it visited. Equals. Well, actually, I'm gonna make it so that it's all zeros. 0 times n. Okay? Good so far? All right.
wait, so this is, in Python you can,
Yeah.
You can do anything.
you can make an array like that?
Yes.
That's,
Yeah.
that's That's so weird.
I know. There's a more efficient way of doing this, which is list comprehension, but this is simpler.
Okay.
I
Yeah.
was doing this for a 2D array, and it gave me a headache because that
Yeah.
repeats like the pointers.
Uh-huh.
This is not like a unique. I don't know how to explain. You know
Yeah,
what I'm saying?
I know exactly what you're talking
That
about.
happened to me. You can do it for 1D array, but if
But for
you
2D,
do like
to replace.
that times n,
Yeah.
it doesn't work.
Yeah,
Can't
those
you just can't you just
That doesn't work, I think.
you need to do that inside of list comprehension.
Yeah, you can do 4.
Yeah.
Like
That does work.
Not for 2D.
That works.
It works. The 2D array,
It
but
would be, yeah.
Yeah.
when you modify just one row, it modifies every single
Yeah.
row.
It's really
Because
weird.
the way it does it is
Hmm.
it keeps the reference at the same.
Yeah.
Oh, that's weird. Oh, okay. So it's basically just m references to the same array.
Something like that.
That's kind of strange.
can't you just do it in like a loop and then
That's
append it
garbage,
to-
dude. That's garbage.
Yeah, who wants to do a loop or Python? We need one line and that's it.
No, but you can do this comprehension with loop.
Yeah, you can do.
No, not plus.
you can do 2D
Not
with
plus.
list
Not
comprehension,
plus.
I for I in range n, for j in
And
range
Yeah.
n, and between two
Yeah.
brackets.
You're right.
okay. What was I? Okay, yeah. So I'm gonna make a DFS on index, or I'm gonna call this room actually. Okay. So what do we need? Right. So going to each room, we say that equals.
Remember, they're supposed to solve it.
Oh yeah,
I know
right.
you can solve it.
Oh yeah, I can solve it. Okay, what do we do? What do we do, guys? What do we do?
We have to create the adjacency list or as rooms already done this. Like
Yeah, we don't. Apparently, we don't need an adjacency list, because
each key, a key
Yeah.
in each room is the index to the next room.
yeah, so you don't need it.
So you
That's
can look at it
you're.
as-
This is already an adjacency list.
Yeah.
Yeah,
So
you can look at it like
you
that.
could literally just iterate through the 2D array,
Yeah.
right? And then if you, whatever value you find inside is the index to
Yep, the next room.
to the next room, and then in the array of rooms, you just set that to 1.
Okay.
So if you go through those, 4 is going to be 0 at the end. and
Right.
When you find it, it's going to return 0.
So what do we do now here, right? What do we do first?
Well,
You
is
should
this,
set
is
it.
this really DFS?
It is.
It is?
It is.
Or
Yeah.
wouldn't be.
I mean, you're not really going. I
No,
mean,
yeah, you are.
You are?
Yeah.
I was thinking just like literally just linearly iterating to the array, like from 0, and then so like you start 1, 2, and then 2, but that's already 1, so you keep going, then 3, that's another 1.
Let me see if that's possible. You could do this DFS though, but let's see what you can.
Okay, but let's actually go
Yeah,
on.
okay.
All right. So what do I do here? I'm not done with this line.
Makes sense what you said.
This is an integer, by the way. It's one of these values.
I'm with Python.
Okay, no, but DFS. What do we put in DFS? First line.
It's child, like one of its children, right?
But before that, because it could be its own child.
No, you can't do that.
You can.
And what if there's, you don't
So
have keys
you're
to one
using the
room?
base case? Is that what
It's
you're
gonna still be 0.
Well, before we explore, the children of this room, what do we need to say about this room?
If
Oh,
it's
wait a minute,
different
but you
from
don't
ours?
say you already saw that you just
No.
did it.
Yes,
Yeah.
we visited it.
Okay.
We need to make sure it's
That
visited.
matrix
It's
tells
all.
you what keys you have.
Yeah.
So we say 1. 1 means it's visited. So first we have to say that room is visited.
Oh, okay.
Then we iterate through the list, right? For key, right? We're gonna get the key, right? And the amount of keys that are in, we call this rooms. In, I wonder if this is gonna give me an issue. Should I make a deep copy of this so that it's here? Because this is like a, oh no, oh this, will this actually give me problems?
No, why?
It won't. Okay. All right. Yeah, it won't give me problems. So what do we check about the key? Okay. But we need to do something. We need to check. Yes, exactly. So if self dot ted key does not equal 1 or it equals 0, I'll just leave it like that. Then you DFS on key. Okay? Yeah? All right. So just do that. And once you escape and we're done, well, actually, we made the function, right? What do we call DFS on? On what?
0.
Right. And why 0? Yeah, because that's where you start. That's the only room that is unlocked. So you call it on 0. And so, so now what do we need to check? We need to return true or false. Right. So now we need to iterate through visited. So for v in self dot visited, if v equals 0, return false. Now, if we go through the whole thing, if we don't find a single 0, that means they were all visited. So return true. So this is one problem. Is that Google gave you this?
Yeah, like when I first switched to CS.
Hmm.
It's not nice.
Oof. But you didn't know this.
No, I didn't know what DFS was.
But if you took it the assessment again, right?
Easy.
Right? Easy. Okay,
Your
but
lecture.
don't flatter me, please. Please, please. So I think we can do all this in one line, though. This whole thing in one line.
Yeah, it's called all.
Huh?
The all function.
All?
Yeah, ALL.
Oh.
Parentheses, and then pass self-not-visited.
Visited, self-visited.
Yeah.
And what do I say about it?
If everything in there is true,
All
it
equal,
returns true.
no, 1. 1 or 0.
I think it's gonna amount to the same thing.
Well, what if I was thinking just like, instead of this, we would sum it up, and if it's equal to n, then it's true.
Okay, that was the same.
I mean, it's just my huh? Yeah,
Yeah.
that's still all one, yeah. Return sum of self dot visited equals to n, right? Because if they're all visited, if it's 5, then it's 5 ones, so it's 5. Okay? And if it's not equal to it, then it'll return false. That's good? That makes sense? All right. Oh, this is a fun problem. BFS? Okay, so now BFS. Let me see.
Then GDSC.
Hmm?
Greedy first search. No, okay.
G. Man, what a pranker. You're such a pranker. You're a pranker, you. You are a pranker. Okay.
ASS. That's not a good acronym for that.
Okay. So we still need this.
So let them do it. Don't
Okay,
do anything.
fine.
Just let
All right,
them-
fine. You guys solve it. Come up here and solve it.
Oh yeah, someone come up and solve it.
Yeah, that should be a nice change of pace. Who wants to do this in BFS? Who remembers BFS? You don't remember BFS? No
I
way.
mean, I know like the idea, but not.
Let's start it. One of you guys. Go. You guys know the idea?
Okay.
Start it. Oh, Paulina.
Somebody. Yeah, Paulina, you know. Come up here.
I don't remember, no. I just.
Okay. So instead of going recursively down the path, you go by level. All the levels are together. Remember now. So in order to do that, you need a queue. And not a priority queue or a min heap. I mean like a regular, good old queue. You know? Or a deck, as they would say. So we need to import. Usually when I use a queue, I just use a regular list in Python. However, as Lazaro has mentioned before, that doesn't quite work out because it's like it's a linear time to remove it, to pop it. So a deck has, so I make a queue, right? Queue equals deck. I'm gonna make a deck object. Is how you instantiate it, or do you need an actual list inside there?
I think you need this.
So just a random empty list. Okay. So you create a deck object that you imported from deck or DQ. I'm just saying deck because that's how Patrick pronounced it. Remember? Patrick?
I've heard it as that.
He was in like France or something.
Oh yeah.
He pronounced it as deck. So okay, so we start at 0, right? And we put q dot push 0. All right? So we're pushing it to the queue. What do we do next? Hmm?
Is it NQ?
No, this is going to be linear. This is actually, you know what?
Like the method.
We don't need this anymore. Okay. The method?
Yeah.
It's going to be linear. You're only going to go through each node once.
I mean like push. I don't think in that the method is push.
No, deck is in a class. Actually, no.
I think she means append.
Like instead of push, I think it's called NQ.
What's it called?
Yeah.
No, I think it's append.
Is it
You
actually?
want it added to the back, right? And then remove.
Is push added to the front? We want it to add it to the back.
No, the way I did it, I used append.
Okay, so I'm gonna append.
Because we want to add it to the back, right?
Yeah, it's a pen.
Yeah.
It's append? Okay, so it's append. Now what do we do? We had a queue, we appended 0 because that's the one that's unlocked, then what? The next thing.
NQ is,
Go on.
Can you explain why you're using NQ?
Because here's what we're gonna do, right? So we're exploring. Zero. We have a queue. Okay. So they enter in this direction. Well. Okay. Just say we keep adding to. No, that's gonna make it look like a stack. Never mind. Hold on. They enter and leave in the same direction. I'll put it like that. So here's what the first one. What's the first one we're going to put in the queue? So we're going to put 0. Okay. Now, 0 has 2 adjacent ones, right? 1 and 2. The first one is 0, right? And 0, we've already visited all the adjacent ones. 0 is visited. We don't need it anymore, so we pop it. Okay? Now we move on to the top of the list, 1. 1 has no adjacent ones that, well, I mean, it has 2, but 2 is already in there. Actually, that's just gonna make it weird. Okay, the idea is you pop it, go to 2. 2 has 1 that hasn't been visited. That's 3. You pop 2, and then you pop 3 because it has no adjacent. Then the queue is empty. And when the queue is empty, that means you're finished. Does that make sense? Are we finished when the queue is empty? Okay. So what we need to check, we're gonna loop it, right? While queue. And this one checks that it's not empty. It's an object with things in it. Okay? Okay. So what was it? What were we doing exactly?
Didn't you look at all the nodes adjacent to 0? Or like all the...
Okay. But before we do that,
We add them to the visited and then to the queue. And we pop the first element.
okay. So let's start at the beginning. We're at 0, right? At the beginning, it's just 0. That's at the top. So we want to get that value. So what happens if I pop? What do I get? Is it pop left? What happens if I pop left? What's going to happen?
It's going to end.
Well, no. It's not necessarily going to end. It's going to remove it, but I'm going to store it in a variable as the current one. So I'm going to get the current one by popping left. Equals q dot okay. And then I say that visited cur is a number. I mean, we're just putting numbers. Does that make sense? We say it's visited. Okay, then what?
Append their child. The child is
Okay. With what condition? With a for loop? Okay, yeah. You're actually right. For key in all right. When do we append it? Yeah, exactly. So if not and so there's a little special neat little trick, right? Since nodding a 0 makes it a 1. Nodding a 1 makes it a 0. Actually, nodding any number makes it a 0. And nodding 0 makes it a 1.
False value.
Huh?
It's false. 0 is false.
Yeah. 0 also means false. Because it hasn't been visited. So if you're not a false, it makes it true, you call it. The if statement runs.
Yeah.
Okay. So what do we do, right? What we were doing before is that we push, we append. If it's not visited, q dot append key. All right? Okay. So then you just continue doing that. That's pretty much it. So actually, I'm curious. Is this gonna append to twice?
Wait, what?
Is this gonna be appended twice? It's gonna be 0, 1, 2, and then 1 is adjacent to 0, but we didn't mark 2 as visited, so we added 2 again.
No problem. Maybe.
Probably gonna happen. It's not gonna be a big deal.
No, I don't think so.
Okay. Okay, it's not a big deal. This is gonna work. And so it's gonna be 2, 2 to 3, pop 2, pop 2 again, and pop 3.
Don't you mark them as visited?
Yeah, we do. Oh, well, I mean, we do it here.
Yeah, when you put them in the queue. So
When they're at the top, when they're at the left. But the left notes, we say they're visited.
oh, I thought you did it before you put them in the queue, so that doesn't happen.
What do you think? Should we do that?
I did something similar to that.
Like you put it in the if statement?
I did it if I haven't seen it.
Okay. That actually makes sense now that I think about it. Okay, so then.
Yeah. Let's go back to it.
Feels a little redundant though. I put visited twice.
Yeah, I did it different too. Instead of adding the index 0, I added the room 0. So that right?
Uh huh.
It doesn't think.
This works.
Yeah, no. I
This works.
Yeah.
Okay, and then it's basically what we did before. And then what? We just return. No. Sum visited equals n. Okay. All right. So this is the other way of doing it. This is the BFS way of doing it. Any questions on this versus the other one?
Did you guys understand it? The implementation of it?
Yeah.
Every time, so is that the way we usually implement DFS?
You use a queue. Yeah, it's non-recursive. I mean, DFS could also be done non-recursively. Quite frankly, I don't. It's kind of a pain. Quite frankly, a pain. I don't want to do it. It's just using a stack, and you just. And it makes sense that you're adding a stack because when you're doing a recursive call, you're adding on the stack in memory. Yeah. So yeah, doing the stack is actually kind of figurative, a metaphor of how programs run recursively. Okay. Now we're done being weird, being metaphoric and philosophical, and looking at the art of some of these algorithms.
Beautiful.
The beautiful artwork. Anyway, so Dijkstra on that.
Next class.
Maybe we could do it next class. Or maybe, do you guys want to do single source or topological sort?
I come here for topological sort.
You'd come here for topological source?
I've seen topological sort 2 and 3.
Okay.
Not by me, but by people. I know.
Yeah. So I guess we'll do topological sort next lecture.
I've seen topological sort. Right? Was it you or Demba?
It was Demba, but
Ah.
me too.
Okay.
But originally not mine.
Okay. Do you want to talk about it?
Oh yeah, I'll do after you say the mobile development stuff.
Right. Mobile development, 7:30. Yeah, okay. 7:30 p.m. in case.
Last developer community.
Oh yeah, this is their last
Showcasing
one.
Projects.
Yeah, they're gonna showcase all the projects.
We like that.
Yeah.
So next semester, is this gonna be on Wednesday still?
Did you guys enjoy it? Should we? Should we stop? Are we bad?
No?
No? You like it?
Yeah.
So this is the
I
first
mean,
time?
I haven't come to every meeting.
Okay, so we
This
can,
is the
yeah.
first time we've done it.
Yeah, this is the first time we do this sort of lectures,
Yeah.
apart from Gary's team review lectures.
Yeah.
So, you know. Okay, so now you want to talk about the feedback form?
Yeah.
Let me give you the mic.
I'm so sorry.
No, don't worry about it. I'm actually ashamed that you couldn't finish networking.
Yeah, it's a good problem, I'm not gonna lie.
Actually, it's a good problem. Yeah, if you never
Okay.
the problem that we gave up on. It's behind you.
What if,
And then give up, like tactically
You wanted-
retreat.
Yeah.
if you just wanted to get from the source to a destination node in the minimum path, you
Yeah.
still have to do the extra?
It's kind of what you have to do. And you get the max.
Or you can make like an optimized,
I mean, you kind of need to use Dijkstra for that one. Well, you
Optimized
can-
Dijkstra's, you said?
like if I just wanna get from node 1 to 4, do I still have to make Dijkstra to all of them? You know?
Well, you don't know which
Oh,
one's your max.
yeah.
You don't know which one's the furthest one.
Yeah, you don't know like which nodes you have to go through to get to that one. So you might have to look at all of them. But if you just want to get from one place to another, no, you have to look at all of them because you don't know what path to take.
So it's still as complex as Dijkstra?
Yeah, you could do like something similar like BFS or DFS. But if you want to be optimized, like if the edges have weights and stuff, Dijkstra's, because Dijkstra's uses a priority queue. And that's, you can think of it as DFS, but sorting depending on the weights. Which is why, I don't know who said DFS. When one of you guys said DFS for solving this problem, you could do it, was you?
I think it was you said DFS to solve the delay.
The first problem, this one?
Yeah.
Yeah, you could do it, but you need to sort it. You need to do DFS, and before you actually do the for loop, inside the recursive function, sort.
That will make it n log n, and
Yeah.
the algorithm is supposed to be.
But make it
n.
n squared log n. Because you're doing DFS. And then inside each DFS call, you're sorting.
Right. Okay, yeah. Okay, yeah. So it will be n times n log n.
Yeah, exactly.
So yeah. So but you can do it in linear time.
Yeah.
Dijkstra's not.
Yeah. Yeah. Okay, anyways, so as I already said this a good amount of times, but this is the first time we've done beginner lectures on Wednesdays. Hopefully you guys enjoyed it, or hopefully you had a good experience with it, and that you enjoyed the curriculum that we've covered so far. We went over a lot of things, but we obviously still want to improve. I have no doubt there's places for us to improve. Like I said, it's the first time, so there's probably things we missed or overlooked. So I just want to ask for feedback, and we have this feedback form here. You don't have to do it now. Like I prefer if you don't do it now. Do it like when you go home and you have time. Because if you could be as descriptive as possible, it really would help us the most, and I appreciate that. So if you guys can at least save this link or just have it in your phone now, or if you're quick doing it now, I don't know, up to you. This will take you to the feedback form. We'll have a couple of questions. It's not that many, it's not that much writing. Most of it you have to choose from a scale of 1 through 5. And I think the last question is the one you have to rate. But it could be as detailed as possible. I would really appreciate it. Because we're just trying to make the best community for you guys. And hopefully give you guys a good job from this, of course.
Yeah.
That's pretty much it. Oh yeah, thanks.